Welcome back to our lecture series here. So, we will begin with I believe our sixth lecture, and as we are going along, I am also learning to work with this software and with the tablet PC here. Let me begin this way today. I have a summary of the lecture on the pad, and maybe I will just zoom in a little bit to make it a little bit more clearer perhaps, and then we will scroll down to see. I think that should be very visible. So, this is a summary of what we did in the last lecture. We first started out by defining equivalence classes defined by starting from a group. One thing I realized after finishing the last lecture was I did not actually mention the word coset. Okay. So, the equivalence classes that we defined, which originated from a subgroup, are actually called cosets. So, I will correct that, and I will begin my lecture today by giving a formal definition of a coset. So, those equivalence classes that arose from groups, we were looking at that, and we looked at the structure of an equivalence class that arises in that manner. We looked at some examples, then we showed that elements in different equivalence classes can be placed in one-to-one correspondence. After that, so with that we were done with groups and subgroups and equivalence relations, and then we moved on to talking about another algebraic structure, namely we are talking about rings, and we laid out what the axioms of a ring were. We looked at ring with identity, commutative ring, integral domain division ring. So, we will pick up the discussion from where we left off in the last lecture, and we will look at some examples. Okay. So, we will do that today, and also I think it might be instructive to also show you what our plan for today's lecture is. So, today the first topic that we will consider is to finish up the discussion on rings and fields by actually providing some examples. After that, we will move on to talking about vector spaces. So, this is taking us into the realm of linear algebra. Again, now of course, some of you all may have had the requisite linear algebra, but I am going to assume that you do not, and then so in some sense this is an attempt to make the course self-contained. So, we will talk about vector spaces, we will talk about the axioms by which they are defined, we will look at examples, derived properties, subspaces, examples, test for subspaces, further examples. Then we will talk about, then we will get back, at that point we will be ready to resume our discussion on linear codes, and we will begin talking about the class of linear codes. So, that is roughly our plan for the day. Now, so the first thing that I want to do today is talk about cosets, right. So, here we have a page. So, this is like trying to take care of something that we did not completely finish last time. So, let me take the discussion back to the equivalence classes that arose from a subgroup. So, in this example that we looked at last time, the relation arises in this way. You have a group, you have a subgroup, and A and B are declared to be equivalent if A times B inverse belongs to the subgroup, and we saw that this is an equivalence relation. Now, we want to then we moved on to give a different description of these sets E sub B. Remember, we defined certain subsets and we call them E sub B. This is the set of all elements that are equivalent to B, but in the case of this particular relation, they happen to be of the form capital H times B. Capital H times B needs a definition because you have a set multiplying an element. So, that is just simply defined as all products in which B multiplies on the right side all the elements in H. Okay. So, these were the things, and we looked at examples. Now, it is precisely these elements that are actually called cosets, all right. So, I think it is appropriate to put this to make a note right here, and I will do it in red so that it stands out on the notes. Subsets subsets of G of this form are called cosets of H in G. So, this set is an example of a coset. When the group is the integers mod 6 and H is the even subset of Z6, then we saw that the cosets of the subgroup, there are only two of them. One coset is 0 to 4 and the other is 3 1 3 5. So, again trying to bring in the notation, the terminology of a coset. So, this subset here corresponds to the coset H plus 0, and this subset here corresponds to H plus 1. Now, you might ask, I thought you defined it as HB. Well, that is because our operation here is addition. So, H times B gets replaced by H plus B, and in this case it turns out that there are only two cosets, H plus 0 and H plus 1. Then we also looked at another example in which, so in this example the group itself corresponds to the set of all binary 7 tuples. The subgroup is the even parity or the single parity check code, and then it turns out that the equivalence classes or the cosets are just C and C plus 0. So, again this is the coset, this is the coset C, and this is the coset, C plus this vector, this particular vector. Right. And I think perhaps we have too many arrows. So, let me just erase this and all right. And also the further on we actually showed that the equivalence classes, there is a one-to-one correspondence between elements of different equivalence classes. So, you can also rephrase that and say that there is i.e. there is a one-to-one correspondence between the cosets, the cosets of H in G. All right. Okay. So, I think with that I have remedied my oversight in not introducing the coset terminology like last time. So, with that we will continue on the topic of rings. So, where we left off last time was we had defined these various kinds of rings. There was the ring with identity, the commutative ring, the division ring, integral domain and a field. Okay. So, now let us move over to our current lecture. Okay. So, our current lecture we began with this overview, and I have reproduced here for the sake of convenience this ring diagram that we had last time. In terms of examples, we put down certain examples R, C and F2, and I also thought it is good to say a few words about F2. Now, so here F2 is just the set 0 1 or that is one way of looking at it, but you could also look at it as a field. It is also a field if you think of it as F2 plus and multiplication, and we had written down some time back tables governing how addition and multiplication take place. And again I thought that just for the sake of clarity I am going to actually reproduce that here. It will not take more than a minute. Okay, so, this is under, let us say plus, so you have 0 1 0 1, this is dot and you have 0 1 0 1 and oops. So, this when you add you get 0, you get a 1 and a 0. So, this is because you are doing modulo 2 addition, and here there are no surprises, this is 0 0 0 and 1. Okay. Now, it turns out that this set along with these two operations satisfies all the conditions to actually make it a field, and further being a field it has only 2 elements. So, it is called a finite field. In fact, it turns out that amongst the class of finite fields this is the smallest possible finite field, all right. So, so let me just make a note of that. Can verify that the set 0 1 along with the operations above defined as above forms a field. All right. Okay, so again that was a clarification. With that now, so that means that we are now clear why it is that we have these 3 examples sitting here. So, on the topic of rings I would like to introduce some other examples as well. So, further examples of rings. Let us take one, the set. So, I mean in terms of listing we have already seen R, C and F2. So, these are all fields. So, in terms of saying well what kinds of rings are these, we have already seen that these 3 are examples of fields. then you can also look at Z, the set of all integers, all integers. So, that means that you are including positive, negative and the element 0. So, what kind of a ring is it? So, let us go back and look at this figure here. So, certainly you can check that it is a ring. Okay, so here I guess I should point out that of course, when you talk about a ring, strictly speaking one should specify the operations, but these are just the usual addition and multiplication, and it is not hard to see that the axioms of a ring are satisfied. And further, you can also certainly we know that multiplication is commutative, so we have no problem there. And in fact, it is also an integral domain, because if you multiply, the only way you can get 0 by multiplying two integers is if one of them is 0, and that condition is the defining condition for something to be an integral domain. And in fact, the name in the terminology integral domain arises because the integers are the simplest possible examples. Okay. So, in terms of where do we put Z, the most appropriate place to put it is here. Okay. Now, you can also ask, well, why is not it a field? Well, for example, elements in the integers do not have inverses, so you can't actually call it a field. Could you also put Z over here? You could also put Z here if you liked, because the integers do have the identity, okay, namely the multiplicative identity, which is 1. So, it is this and this. So, it is an integral domain, it is a ring with identity, but it is neither a division ring nor a field. Okay, 3. Now, let us make a slight variation and actually define 2Z. So, what is 2Z? 2Z is nothing but the set of all elements 2 times little z, where little z belongs to z. So, in other words, this is all even integers. Okay. By the way, we already decided that this was an integral domain. Right. It is also a ring with identity, but I will not mention that here. Then 2Z is a set of all even integers. Okay. So, let us now go back. I think I have a way of going back. Okay, here we go. So, if you look here, then certainly it is a ring, and even the even integers they are commutative, but in terms of them, if you ask the question, are they an integral domain? Yes, they are an integral domain, but are they a ring with identity? So, the difference between Z and 2Z is that 2Z can be listed here, but 2Z cannot be listed as a ring with identity. Now, let us then move on to a different type of example. Supposing you consider the set of all m by n matrices over the real numbers. Okay. So, this is the set of all m by m n matrices over the reals. So, what we mean is that all the entries of each and every matrix is a real number. Now, so strictly speaking, when we talk about a ring, we mean R m cross n, multiplication, addition. Addition is defined component wise, multiplication is the usual matrix multiplication. So, now let us go back and check which properties are actually satisfied. Is it a commutative ring? No, because matrix multiplication is not commutative. Is it a ring with identity? Yes. So, you can actually put that down here. It is not a division ring because a matrix in general does not have an inverse. So, we will put that down here. Okay. Next example. We are going to define f rectangular bracket x. Okay. This notation denotes the set of all polynomials in the indeterminate x over f. Okay. So, another way of expressing this is to say that this is the set of all expressions of the form the summation k goes from 0 to d a sub k x to the k, where the a sub k belong to f and where d greater than or equal to 0 is an integer. Okay. So, this is what we mean by a polynomial in the indeterminate, and this d is called the degree. Okay. So, make a note of that. So, again you have to when you talk of a ring you have to introduce operations. So, oops. So, we are speaking of f x plus and this. Okay. So, what do we mean by addition of polynomials? It is the usual addition. If you add them component wise, and multiplication of polynomial also takes place in the usual way. So, most of you all are familiar with this, so I will not spend time on it. So, let us go back to the interesting question of where would you place this here. So, as a ring you can verify very quickly that it is a ring. Multiplication is commutative. How the order in which you multiply two polynomials does not make a difference. It is also an integral domain, because if you multiply two polynomials you cannot get 0 unless one or the other is the 0 polynomial. Okay. Now, that is not immediately obvious, but if you just sit down for a couple of minutes you should be able to see a way of proving that. Is it a ring with identity? Yes, because the polynomial which is just the constant 1 is the identity. Is it a division ring? No, because for example the polynomial x does not have an inverse. Okay. So, here again we would put this here and here, right. Okay. So, we have seen examples. Now, so if you look at this figure, there are two gaps in some sense. So, what could we put in here and here? So, in other words, we are looking for a commutative ring which is not an integral domain. So, this is example 6 then. So, consider Z 6 under multiplication So, so addition and multiplication take place modulo 6. So, you can check that the defining axioms of a ring are satisfied. It is commutative, but it is not an integral domain, but because 2 times 3 is equal to 0, therefore, it is not an integral domain. Okay. So, in this figure we can put down here Z 6. Okay. So, now we have one entry less to fill, which is a division ring. That is, we are looking for something in which it is a ring, the ring has an identity and every element has an inverse. The only thing that is not missing is that multiplication is not commutative. So, I will not actually go through this discussion, it will take us too far away from our subject, but an example of this is Hamilton's quaternions. And it turns out that now this seems like pure mathematics at this point, but it turns out that extensions of Hamilton's quaternions have actually found application in wireless communication, and certain very efficient space time codes for multiple antenna communication have been constructed using objects which are generalizations of the quaternions. Okay. So, with that we are done with the topic of rings and fields. So, now we will move on to talking about vector spaces. So, definition: a vector space V plus is a set V of vectors a field f of scalars and two operations plus, which is which we will call vector addition, and dot, which will be scalar multiplication such that the following properties hold. One, V plus is an abelian group . Two, C times V is in V for C in F, V in V. So, there is a distinction between the capital and the lowercase v. So, here so whenever we introduce a vector, we will put a bar underneath it. So, this is the axiom of closure. So, this is closure under scalar multiplication. Then if you take C1 times C2 V, that is the same as C1 C2 times V. So, this is associativity of scalar multiplication. Next, you have the distributive laws, which say that C1 plus C2 times V is C1 times V plus C2 times V, and that C times V1 plus V2 is C times V1 plus C times V2. So, these are called the distributive laws. The final axiom says that if you take the element 1 and multiply any vector with it, you will get the vector back. Okay. So, this is how this is. All these the axioms 2, 3, 4 and 5 are telling you how the scalars interact with the vectors. So, one is telling you that if you multiply a scalar and a vector, then you will get a vector. This multiplication is associative, it is distributive, and if you take the identity element in the field, because we know that the scalars form a field, so there is a multiplicative identity. If you take the identity element in the field, then and multiply it into a vector, then that vector will remain unchanged. Okay. So, it is worth just pointing out here that this is the multiplicative identity. Right. So, these are the axioms that go to defining a vector space. So, if you keep in mind that in order for something to be an abelian group, it needs to satisfy 5 condition. This makes for a total of 5, 6, 7, 8, 9. Okay. So, there are a total of 9 conditions that need to be satisfied. So, what are some examples? The most common example are vector spaces of the form R to the n, where strictly speaking we mean R to the n is the set of vectors. This is ordinary vector addition. The scalars are the real numbers and you have multiplication. Okay. So, for example, when so this is an example within an example. So, here if you take n is equal to 3, then you can actually draw a geometric picture. So, a vector would then let us say that this is the point, this is the origin, let us say, and that let us pretend that this is the point whose coordinates are 1. So, this is the x, the y and the z axis. So, 1, 3 and 2. Okay. So, then this line here would represent the vector 1, 3, 2, right. Okay. So, that is and you can verify that this forms a vector space. Similarly, analogously, you also have the vector space f2 to the n addition f2 this. So, this is the analog of the vector space with the real numbers, except that you replace the field of real numbers by just the set of all binary n tuples. You can also look at the set of all polynomials over a field, where the field defining I mean it is the same field, the scalar field is precisely the coefficient field of the set of all polynomials. And you can even think of the set of all m by n matrices as forming a vector space. Again, I think for lack of time I will not actually bother going through the verification process. I think addition and multiplication, the definition in every one of these cases is fairly straightforward. So, you just have to go through the axioms and verify for yourself that they are actually satisfied. Next we will actually go through some list some derived properties. And I think part of the reason for going through with this is because whenever you think of a vector space, there will be a temptation on your part to actually think of a particular vector space, perhaps 3-dimensional space or 4-dimensional space, but sometimes you need to get away from that and think only in terms of the axioms. So, you have to just think very logically and not fix your mind on any particular example of a vector space. So, in going through a proof of some of these derived properties, it will turn out that that process is an exercise in thinking along those lines. So, one of the derived properties states that if you take 0 and multiply a vector with it, you will get the 0 vector. Okay. So, what does 0 here mean? This 0 is the additive identity in the group V plus. Okay. On the other hand, this 0 here is the 0, the additive identity in F, okay, or more precisely in the field F, in the field F. Okay. So, the two zeros are different, and now we are saying something about how they interact. We are going to say that if you take the scalar 0, multiply it into a vector, then you will get the vector 0. Now, if you are saying this for the first time, you will say that is obvious, it is kind of stupid trying to prove that, but that may be because you are fixing your mind on a particular vector space. Here we are saying we want to prove it for all vector spaces. So, we need to only work only with the axioms. So, the proof of this will proceed like this. If you take 1 plus 0 times V, then this will be 1 times V plus 0 times V, which will be okay. So, let us leave it at that. On the other hand, this is 1 times V, because 1 plus 0 is 1, which we know from an axiom is equal to V. So, now we compare the two, and we see that by the way, even here I can take this a little bit further and say that this is V plus 0 times V. So, now adding minus V to both this expression as well as this, to both V plus 0, we see that 0 times V is equal to 0. Okay. So, this is typically how proofs of this kind will proceed. So, I will, in the interest of moving quickly, I will move quickly through the proofs of the other properties. If you take C times the 0 vector for any scalar, then you will recover the 0 vector. Okay. So, how do you prove that? C times 0 plus V is on the one hand C times 0 plus C times V, on the other hand that is C times V. Therefore, C V is is C 0 plus C V. So, what we can do is we can add the additive inverse of C V on both sides. Therefore, C times V plus the additive inverse of C times V is equal to C times 0 plus C times V plus minus of C times V. So, you should read this as the additive inverse of C times V, right. And now, of course, this gives you 0 vector on the left, because you take any element and add its inverse, you will get the identity. Therefore, 0 is equal to C times 0, okay, and we are done with that proof. So, to summarize, what we have shown is that C times the vector 0 is 0, and we also showed that the scalar 0 times any vector is 0. Now, the third property says C times V is equal to 0 if and only if either C equal to 0 or V equal to 0. So, proof: if C equal to 0, we are done. If C is not equal to 0, then consider C inverse times CV, which is equal to C inverse times 0, but we know that any scalar that multiplies 0 will give us 0, right. That was what we just proved. But on the other hand, this is C inverse times C times V, which is equal to 1 times V, which is equal to V. So, now you compare these two and conclude therefore, that V is equal to 0, right. So, I am going through these a little bit fast, but I am going to assume that you will have some time to look through the notes on your own afterwards and make sure that you understand the proofs. Then as an exercise, you can try to prove that minus 1 times V is equal to minus V. Okay. So, that is something that you might want to try to prove on your own. All right. So, we are done with derived properties. Now, what we want to do is look at instances when a larger vector space contains a smaller vector space. So, I will illustrate with a picture. So, supposing you have something like this. Okay. And then you have and let us say that this thing here is a plane that passes through the origin. So, in this case it turns out that so this plane is sitting inside 3-dimensional space, which is a vector space. It turns out that the elements in the plane also, by the way, when I draw this plane I mean an infinite plane. Okay, so, this is the diagram in that sense is misleading. So, there is no limit, it is the infinite plane. So, if you consider all vectors in the plane, such as for example this. Okay. So, I mean that this plane for example includes vectors like this, vectors like this, vectors like these, and these vectors could have infinite length, right. So, then this is also a vector space. So, when you have one vector space sitting inside another, this the smaller vector space is called a subspace. So, that is our next topic. A subspace of of a vector space is a subset W of V such that W plus dot F is also a vector space. So, what are some examples? In R3, that is in 3-dimensional space, possible subspaces are one R3, all of R3, just the origin, any line through the origin, any plane through the origin. Okay. So, these are the only possible subspaces of 3-dimensional space. Now, just looking ahead a little bit, you can explain why there are only these kinds of subspaces, because later on we will attach a measure to a subspace, and that measure is called dimension. Now, R3 is in everyday language called 3-dimensional spaces, but in a very formal mathematical sense it is an algebraic object that has a dimension of 3. These to these subspaces also you can ascribe dimensions. So, each of the four items that we have listed below corresponds to a different dimension. So, R3 is 3-dimensional, the 0 vector is of dimension 0, any line is dimension 1, any plane is dimension 2. Okay. So, that is why these are the only kinds of subspaces. Again, I am going to leave it to you to verify that that they are actually indeed subspaces. The next topic is, how do you test for the presence of a subspace? So, we are in the setting where you have V plus F dot, and then you have W plus F dot, and W is given to be a subset of V. And you are given that this is a vector space and you want to test, is this a subspace? Okay, so, that is your goal. Now, one way of testing whether something is a subspace is to actually go through all the axioms, and as I pointed out earlier, there are 9 of them. But that is the brute force way. It turns out just like along using an argument very similar to the argument that we used in the case of groups, you can show that you can actually reduce it to a single test. Suffices to test turns out. To test whether or not W is a subspace of V. Now, I should so let me just put this in quotes, because strictly speaking it is not W that is a subspace, it is just this entire W plus F dot, okay, but that is too long to say. So, we will just say that we will abbreviate it to W is the subspace of V. It is sufficient to check that A, I am going to use a different letter, to check that x plus cy is in W whenever x and y belong to W and C is any scalar that belongs to the field of scalars. So, you just can apply this one test, and that in a sense covers all the 9 axioms. Why is that? So, if you ask the question, how does this cover all the axioms?